Good morning, my time. I'm in sunny San Francisco today. Glad that you all signed up and that you're attending. Um, uh, I won't make a big political speech. I'm going to focus on the geeky stuff, but I wouldn't be here if I didn't care. So, um, uh, rules of the road. If you not one nice thing about having such a small group is that you can get your questions answered if you feel like asking them. So please take advantage of that. I if you have a question that comes up as you're as I'm talking, I would much rather answer it right away and have you back on track with the presentation. Whether you agree or disagree doesn't matter, but just tracking. If you have a question, I'd rather have you ask it now and then have you sit there wondering about it. You know, what was that word that he said, or I don't. Ask your questions. This is a great opportunity. So today's topic is software design in by which I mean the internal design of the software. What are all the elements in the design, the expressions, the statements, the functions, the objects, the modules, the files, the directories, the services. These are all elements to me, and how they relate together, how we take a big system and break it down into these elements and how the elements relate to each other. That's the province of software design. Um, I've been interested in this problem for, well, ever since I got started programming. About the time you write the second line of your first program, those two lines have some relationship to each other, and for the rest of your career, you're struggling with those relationships. So the this particular line of research that I'm going to talk about um, really kicked off about 15 years ago. I was invited to sit on a panel of the 25th anniversary of. Do I have a copy here? The Green Book, which is called Structured Design by Jordan and Constantine. And this is the book that introduced the words coupling and cohesion into our vocabulary. So I'd had this book as a college textbook. So, of course, I had not read it. But here I was going to be on a panel. So I thought, I better reread this. So I started reading the book and I got really excited because many of the vague concepts of software design that I had been interested in were laid out very explicitly in the book. The specific definitions of coupling and cohesion, which we've kind of lost, were laid out there. The economic rationale for software design was laid out there. And I thought, wow, I need to bring this back to my community because the examples are dated. You know, there's a discussion of using punched cards for programs, for example. And so I wanted to bring that discussion of software design into the 21st century. It's not so easy, turns out. Software design is a big topic. And it was about 3 years ago that I had a couple of weeks free, and I thought, I really want to do this software design book. Let me get started. See how much I can get done in 2 weeks. So I worked and worked and worked. And here's the thing about writing books. Writing books is all about scope management. You start out, I start out, and this is every time I think, well, here's a topic and it's way too small to fit in a book. So I'm going to start working on it, and then I realize, oh crap, this is like 8 books. Let me chop out a little tiny chunk of it that's too small to fill a book. Okay, so and then I start working on that, and then it blows up, and I realize, okay. So about the third or fourth iteration, I actually have a book's worth of stuff. So what I'm going to talk about today in detail is this tiny little piece of a much bigger topic of software design. But but it's all around the theme. And here was the surprising thing. That first line, when I first started to write the book, the first line I wrote is, "Design is an exercise in human relationships." And I thought, what? That makes no sense. Software design is about coupling and cohesion and power laws and refactoring, semantic preserving transformation. It's not about human relationships. But I'd written the words, so that had to be in here someplace, and I put them on the paper for some reason. Like, what in the world is going on? So here's what I think I mean by that. And I'm gonna start at the largest scale and then work down to the scale that I'm actually writing about today. And I'm going to give you a beautiful view of my shiny bald head in the process. So this outer circle, this represents the boundary between things that geeks can control and things that geeks can't control. So I call the two people here waiters and changers. So the waiters look at some software and they say, "Oh, I want a button. I want an edit button for Twitter," just to pick a random example. Anybody who thinks an edit button for Twitter is easy is kidding themselves. But anyway, so the waiters say, "Well, I want an edit button for Twitter, but I don't know how to program, so I have to wait for the changers, the people who can actually go in there and change the code, to implement stuff." And there's a relationship between waiters and changers that's oftentimes tense. Waiters say, "Well, why does it take so long?" Every once in a while they say, "Oh, wow, that was fast," but that's more unusual. The changers, the geeks, the people who actually change the program, they feel pressure. They always need to do the next thing, the next thing, the next thing. No matter how fast they do stuff, there's always even more to do. This is one of the lessons of successful software, is that every feature you implement creates two more features. So no matter how much you do, or how much the team grows, or how fast they go, or how hard they work, or how good the tooling is, there's always too much to do on the changer side. So this relationship can be productive, but it can also be very dysfunctional if the two sides of this relationship don't understand each other. And I'm not going to be talking in my prepared talks about this relationship because it's too big. I don't understand it well enough yet. I'm happy to answer questions about it, and I can answer in principle, and I can apply some of the theory that we will be going through to software design on that scale. But this isn't the main topic. There's another set of relationships, though, inside the circle. So if we have a bunch of changers, say this is a software team, they're affecting each other all the time with their software design decisions. So if I have an API, you're calling it, I want to change the API, now I'm asking you to do more work. Ugh. Yeah, but you're busy. You already have too much to do. So you and I, as fellow changers, have a human relationship, and software design decisions affect that human relationship as well. So how can we look at software design as a discipline that enhances the human relationships within the team? So that the largest scale, we want software design that enhances the human relationships between waiters and changers. Inside the circle, we want a style of software design that enhances the relationship between the changers. And what does that look like? So, for example, if I make a software design decision that causes you work, if I help you do the work, that's a whole lot more likely to end up with a good relationship than if I just say, oh, that's deprecated. What's wrong with you that you're still calling that old thing? I'm shutting it down in a week and you better get your stuff done. And you think, well, that's not my highest priority. So this is another set of relationships, and these relationships are in some ways easier because waiters and changers have very different perspectives on the world. Changers and changers seems like it's a little bit closer, but in fact we're all humans, and everybody's is different from everybody else. So even changer to changer relationships can be fraught and difficult and challenging. And if you've ever developed software on a team, you've experienced this to one degree or another. This is also not the topic for today's talk. I had told you I had to keep shrinking the scope down to something that I could actually talk about comprehensively. And here's where I got to. This is me. Here I am, happy programmer. And I have a relationship with myself. And until I have a healthy relationship with myself as a programmer, I can't possibly have healthy relationships even with other programmers. And so this is the foundation. This is the origins of the scope that I'm talking about today and in this book that I'm writing, and I'll tell you more about that. And here's the key question. I'm about to change some code, and the structure of the code is such that it's difficult to change. Should I tidy first? So I'm not talking about big refactorings. I'm not talking about splitting a monolith into microservices and all these grand and glorious large-scale decisions. I'm talking about my relationship with myself. I have some code. It's kind of icky. I need to change it. Oh, but I have to change that too. And and what does this really do? And am I going to break something? And I feel very uncertain in that moment. Sometimes the right thing to do is say, time out. I'm going to tidy this code up before I change it. So I'll tidy the code up. And then what do I do then? Do I submit that as a pull request, or do I go on to make the changes I want to make? Those are interesting questions. But this is fundamentally about my relationship with myself. Am I worth it to make my job easier to do? Or, and this is there's this masochistic strain of thinking and belief in software development. The code was hard to write, and that's because I'm a heroic programmer and I can slay the dragon with my vast mental powers. And the programming should be anxiety producing and fear producing, and you shouldn't feel confidence. You should be on the edge. And as I've gotten older, I realized, well, what a waste. Now, I had the advantage that I was not a very good programmer. I was thinking about this. I've gotten back in touch with some of my college buddies, and I was reminded of the project that we did. We had a 5-person team, and we had to build a project, and we built this really cool space trading game called Star Trader. And of the 5 programmers, I was the 3rd best. And I knew that I wasn't the best programmer there. And so very early on, I had to develop habits that let me take complicated things and break them down into simpler things. And those habits turned out to be extremely useful. You can only scale your one brain just so far. And it's much more difficult. Once you get to a certain level of complexity, you can't handle one brain just understanding the whole problem, can only get to a certain scale. But the tricks that you use to break down complexity into simpler things, like this habit of tidying first, instead of changing complicated code, I'm going to tidy up what I'm doing. Those habits scale very, very well, it turns out. And so those are really, that's the foundation of what I do. There's a phrase, Mick at Mac, that I came up with maybe almost 10 years ago now. Make the change easy, then make the easy change. And making the change easy is the province of software design. So rather than go and change some hard, complicated thing where you have to make changes in 100 parts of the system at once, you can tidy first, simplify the cost of making all of those changes, and then just make an easy change. Now, it is very hard work to make the change easy. That's the trick here. I'm not saying, oh, making programming easy. Well, it's not easy. It's really hard to make it easy. And so it's still an intellectual challenge, but it's an intellectual challenge of a different order. So part of the, let's see, current template. Part of the what I realized as I was writing about this, one of the great things about writing is you have to understand things really, really clearly, or it just doesn't work. So one of the things I realized is that there are two loops we're working with. You go from an idea. Okay, I need the edit button, to a change to the behavior of the system. Okay, now there's a button like this. There's this user interface, and there's this workflow, and there's a back end to support this. So as we're implementing stuff, we're changing the behavior, the externally observable properties of the system. And one of the frustrating things about software, frustrating and magical things about software, is every time you change the behavior of the program, that's that cycle where every feature spawns two more features. Now we're going to get more ideas for what to do about the system. And if that was all there was to software development, it would be relatively easy. But there's a parallel track. There's a under the water that's also going on, and that's the structure of the system. And the structure is how the whole big thing is broken down into parts. Now, while the program's running, it doesn't care about the structure. If I have one big function or 25 small ones, it just doesn't matter. The user's going to see the same behavior. But the next time the programmers want to change the system, the structure is going to matter a lot. So sometimes when you go to change the behavior, you say, oh, I don't like the way this is structured. If I restructure it, this is the tidy first. So I go from my idea to a change in the behavior, and I think, oh, this is going to be hard to make this change, so I'm going to jump down here and I'm going to change the structure first. That's a common flow for ideas. Now, while you're changing the structure, the behavior isn't changing. So the waiters get very impatient about when is this going to happen. Sometimes when you change the structure, you get more. So I've gone from idea to behavior to structure, and now that the structure is right, now I can change the behavior. And so that's a common flow. And in the tidy first world, where we're talking about little tiny design changes, this should be happening many times a day. One of the magical things about software development, though, is that the structure can suggest ideas itself. So at Gusto, my employer, we had a tax engine, so we issue 1 million paychecks, uh, probably every month, something like that. Um, yeah, 1 million paychecks a month. So we had an engine for calculating taxes, which in the United States is incredibly complicated. And we refactored, we changed the structure of the system so that that tax engine was more separable, more pluggable than it was before. And then someone said, oh, we have this tax engine. We could put this on, use this for marketing material so that you can come to the Gusto homepage and you can type in all of your particulars, and it'll tell you, oh, and this is the paycheck that we would issue in this case. And if somebody just wants to sit there and every month they want to type in all the numbers, they can do it. Or they can sign up for the service and pay us, and we'll do it for them. So that's a case where the structure of the system itself introduced new ideas for changes to the behavior of the system. And if you can run all of these feedback loops together, you can very quickly explore all the different ways that your software can create value. And that's what we want to do. Now there's dysfunctions here. There are styles of development that just focus on idea to behavior to idea to behavior to idea to behavior. That's the feature hamster wheel where as a programmer, you're just implementing features. And it gets harder and harder because you're not paying attention to the structure. There's another dysfunction when the geeks are in charge and in control, and they just focus on the structure and they say, let me get this all right before we start implementing anything. Well, then you implement a lot of structure that is aesthetically pleasing or intellectually pleasing, but that doesn't actually matter for the behaviors the users care about. So you're making investments with no payoff, and you're delaying feedback. So that's big design up front. And what I'm advocating here, and which is consistent with the last 30 years, is a little bit of this, a little bit of that. That there should be a rapid iteration, but in all of these feedback loops, we should be able to try out ideas quickly. We should have those ideas generate more ideas quickly. When we're implementing something, if a different structure would be better for that behavior, we should be able to quickly go change the structure, then finish changing the behavior, except that's going to suggest more structure changes. And sometimes those structure changes are going to suggest new ideas for the system as a whole, and that leads us in a whole new direction. So being able to do all of these three activities in teensy weensy slices is I think that's what creates superior value. All right, so let me talk about some specific tidyings. So what is a tidying? A tidying is a teensy weensy, cute, fuzzy little refactoring. That is, it's a change to the structure that's going to make it easier to change the behavior. But problem with refactorings is they seem like big things. People argue about, well, do refactorings go on the backlog? Shouldn't have a backlog, but that's a separate conversation. Do refactorings go on the backlog? Oh, I need to spend 6 months refactoring this before I can change it again. It's a big, heavy blah, 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 blah. And so people just don't do it at all, and I think that's a shame. So this tidy first work is an attempt to make changing the structure of your code not intimidating. It's just a cute, fuzzy little change that you make so that your code's easier to change. So here's an example, specific example. I like this color. Let's say we go and we look, and there's a great big function with a whole bunch of lines in it. And we think, ugh, what is all of this doing? So we start reading. Before we can change it, we have to start reading. We have to understand it. So we start reading and we're like, oh, I see. There's really three things going on. So the simplest tidying there is I take that and I break it into 3 chunks. Just put in white space. That's the tidying. Now I'm done. Foof. Ship it. Now I can go to production. Doesn't really need code review. There's no risk there. So if I'm changing a big glop of code and I realize that there is some implicit structure and I reflect that structure, even just with white space, I've made my job of changing things easier, because I might be able to say, oh, I need to change this stuff, but then I have to worry about how that might affect the stuff afterwards, but I don't have to worry about this stuff up here. So just breaking up code is a simple tidying. Here's another one. The code looks like this. If some condition, and this is right at the beginning of the function, the if is right at the beginning of the function, and then there's a whole bunch of stuff that's indented. And sometimes there'll even be multiple levels of this at the beginning of a function. And the tidying is to say, okay, when I see an if and I go into the consequent part, I'm keeping in my mind, what the condition was, and I'm waiting for an else. But there's lots of code that looks like this that doesn't have any else. So I'm holding too much stuff in my head. So the tidying here is called a guard clause, where I say, if not that condition, return. If not the other condition, return. This is a very mechanical process. I can write a syntax tree transformer to do this for me, and then there's all of the lines of code after it. This is called a guard clause, and I argue, there is a little bit of discussion about this, but they're wrong. I argue that this is easier to read. The one on the right is easier to read and understand. The way it reads is, here are some preconditions for the code you're about to read. And if those preconditions are met, the code's never going to execute, and don't worry about it. If statements have this implication that there's a then and an else, and you want to do two different things. In this case, you don't want to do two different things. You either want to execute the code in the body, or you don't want to execute the code in the body. And the guard clause version, for my money, makes that easier to read and understand. Now I can go and change some lines in here, knowing what the conditions, the preconditions are for that code. Now, one interesting thing about tidyings is they tend to flow into each other. Once you learn them as kind of a vocabulary for making your life as a programmer easier, you start seeing them in terms of steps. So I can go from a guard clause here, and now this can become the big bunch of code that I then introduce some white space so I understand what the pieces are. The book currently has about 15 tidyings in the catalog, so I'll give you one more, and if you want, I'll give you the details of how to find the rest of it. The last one is I call it explaining helper. So I have a big bunch of code. There's some part of it that does a recognizable thing. So I have the code before, the code after, and then here I call a helper function. And I name the helper after the intention of the code, not the implementation, but the intention of the code. So again, this chaining property, where we can go from this code to guard clause to separating pieces of it, and then that can lead naturally into, well, let me take the chunk out of the middle and turn that into an explaining helper. So there's the other tidyings are things like an explaining constant, explaining variable, introducing a comment, an explaining comment, deleting a completely redundant comment. So people have said, oh, Kent, you're anti-commenting in code. And that's not true. I am pro-communication. And I'm also pro putting as much information into the code as possible. Because we're all geeks. We all read code. If we can put the information into the code, it's easier to keep it up to date. So if I have a function named whatever, set x, I don't need a comment that says sets the variable x. It's sitting right there. It's that comment is redundant. So it can be a tidying to go through and say, oh, well, maybe these comments were important at one point. Now they aren't anymore. I'll delete the ones that are cluttering up my ability to understand this code. That's a common tidying. So I was hoping, I wasn't sure quite how long this was going to take. 8:35. I'm going to do about 10 more minutes of prepared stuff. Everybody has plenty of Zoom calls. I understand that. And then we'll move to comments and questions and arguments and whatever it is, however it is that you want to engage today. The one piece of theory that I want to introduce at this point is how do I want to say this? Okay, so here's an observation of why software is expensive to change. So the cost of the software is now this was a big surprise. It's the cost of changing the software. I can remember being in college, and this was a big surprise. Oh, we're spending 70% of software development dollars on maintenance. If this was a car and we were spending 70% on maintenance, this would be a bad car. So shame on you programmers for not getting it right the first time. And this seems silly now, but that was very much the zeitgeist. There was something wrong with us that we couldn't do it right the first time. I looked at that, and with something like extreme programming, I said, hey, 70%, what can we get that up to 95, 98% of the cost of the software is changing? And, the people still freak out. They still want to do it right. But they don't know what it is. So that seems like kind of silly to me, but there you have it, people. So the cost of the software is approximately equal to the cost of changing the software. The initial development is irrelevant. And if we want software to be more valuable, reducing the cost is one way to do that. Here's another, so a surprising thing is that not all changes are equal. The cost of making the changes is dominated by the cost of a few very expensive changes. And there's a common experience. You go to implement this feature, it's easy. You go to implement this feature, it's easy. You go to implement this feature. oh, this one's going to take us 2 months. From the outside perspective, all those features looked roughly the same size. It's just another button. Why is this taking so long? Technically, the word for the distribution of the cost of features is it's a power law distribution. It's not a normal distribution where you have, you know, some features are more expensive and some features are less expensive. It doesn't look like this. It looks like this. That is, most features are cheap, and every once in a while you have this outlier feature. It's not an outlier. It's right on the distribution. You have this feature that's really, really expensive. And if you total up these expensive features, the cost of all of these together dominates the cost of all the cheap features together. So the cost of reducing the cost of individual little changes isn't a way to reduce the cost of software overall. It's finding a way to reduce the cost of those really expensive changes. But why? Why are some changes expensive, so much more expensive than others? Oh, and I can talk for hours about power laws, which are really cool. But I'm gonna hold myself back. Here's what makes some changes expensive. I have some element, and I need to change it. So I'm gonna change this guy, but it's linked to a bunch of other elements. Say I'm adding a parameter to a function. All the callers of that function need to change. So the change is now propagated from one element to other elements. And maybe, okay, and here I am, and to add this parameter to this function, I need to change these 3 other functions too. And to change that, and to change that. And so you get this avalanche effect. And avalanche is not a metaphor here. It's the same mechanism at work, where one change triggers multiple other changes. And usually with some probability. So usually one snowflake falls over and that's it, and we're finished. But sometimes a snowflake falls over and then 2 more snowflakes fall over, and then we're finished. But sometimes one snowflake falls over and 3 more fall over, and then 8, and then ba-bum, ba-bum, ba-bum. And the relationship between these elements that propagates change is coupling. That's the definition of coupling. The original definition of coupling is 2 elements are coupled. So element 1, element 2 are coupled with respect to some change if changing E1 implies changing E2. So the change is important. If I change the order of the statements in this function that's being called, none of these guys care about that. Probably, maybe, we hope. But they shouldn't be coupled like that. If I change the name, though, they're certainly coupled with respect to name changes. They're coupled with respect to the types of parameters, the numbers of parameters, the order of parameters. They might be coupled with respect to changes in the semantics of this function. If the preconditions and postconditions change, these might have to change also. So this is the role, zooming back out, the role of software design is managing coupling. And you have a trade-off. The tidyings are teensy-weensy little reductions in coupling. But you have this trade-off. You have the cost of coupling, which if you have very little coupling is very small, but it grows exponentially, literally exponentially, as you go along because of this the way changes propagate in a software system. But you also have the cost of decoupling. So there's always going to be some coupling in the system, and what we want to find is the someplace in this valley, this minima, where we're spending enough money on decoupling to push us down this slope so that the cost of coupling is relatively low, but we're not spending so much on coupling. This is this big design up front where we just design, that you can keep doing that forever and increase the cost of the software. So finding that minimum between the two, noticing when coupling is kicked in, noticing that we need to invest, we need to push further on the decoupling cost side to find that minimum. That's the answer to the question, should we tidy first? It depends on where we are in the cost of coupling versus the cost of decoupling. Now, tidy first being the smallest scale of design changes, the costs are still very, very low. So we don't have to worry about getting them right. We don't, if a tidying turns out to be the wrong idea, you just undo it, and it's not a big deal. They're intended to be small enough that they don't affect the schedule at all from the outside world. But it comes back fundamentally to the programmer's relationship with themselves. I need to make a change. It's going to be hard and ugly. Am I going to value myself enough to make my work easy first before I do it? And to me, that's the real hard part. The details of tidyings, you could have figured out all that stuff out yourself. Most of you probably know most of it already. But that moment of, am I worth it? That's the hard part about software design, is saying, is this relationship worth it to apply my skills to the structure of the system so that I can continue to deliver value through changes to the behavior of the system? Man, that was almost a tweet. Almost got it. And with that, that's the end of the prepared material. I see I have one question in chat. Let me pop up chat. It's the comments after, who wrote this crap, and it was you. Isn't that wonderful? What a blessing. If I look at code 6 months later and I say, wow, I just don't know how to write better code than this, I haven't learned anything. What an awful position to be in. Now, as programmers, we beat ourselves up. We're very, very good at it. We even write programs that beat ourselves up. But in fact, seeing code that's we wrote and knowing we could do it better now, that's a blessing. What a celebration. And we have about 13 minutes for questions. If people want to ask specifics, you want to talk about how this looks like, what this looks like from a management perspective or training, or how this relates to breaking changes into pull requests or code review. You want to ask me about Banjo? That's fine. Any kind of questions in general? Love TDD. Thank you for reinventing it. How popular is it in your company? What do you think is the percentage of developers that do it? I think the percentage, I'll start at the end of that. The percentage of developers that actually apply TDD, which has a very specific definition, and I have to say this over and over again because people say, oh, I do TDD. I write some code and then I write tests for it. It's a thing. That's fine. But it's not TDD. TDD is you write one test, that fails, and you make it pass. And you write another test that fails, and then you make both of them pass. And you keep that cycle going until you can't think of any tests that would fail. That's TDD. What percentage of developers do that? Oh, tiny. Tiny. There was this odd paper that came out the other day proving that TDD had no effect. They took a whole bunch of repos. They looked at the ones that had tests and they said, oh, well, these must be TDD. And they looked exactly like all the code that didn't have tests. And I was like, you didn't, if you're going to pretend to do science, to actually do science. So I think the percentage of people that follow exactly that workflow, write a test, make it work, write a test, make them both work, keep going until you can't think of anything. It's teensy tiny. It can be hard. I'm working on a side project, a new user interface for online poker. I play a lot of poker because that's fascinating. Another whole story. So I'm writing this new user interface for poker, and there are moments when I can't think of a way to write a test for stuff. So I don't. I set up other feedback loops, and then I put the, hey, I need to test this, or I need to test as much of this as possible. I put that in the back of my brain. And when I come back to it, say, oh, if I separated this from that, then this part would be easy to test. This part I still don't know how to test. Okay, now I'm going to make that transformation. I change the structure so it's easier for me to change the behavior. And now I can get back into TDD mode, and then I can cruise doing that. So, if I know how to TDD, I'm going to TDD. And if I don't know how to TDD, then I'm going to do what I have to do to get back to where I can TDD, because I know I can make progress so much faster when I do it. How popular is it at my company? I was walking by, this is pre-COVID, I was walking by two programmers pairing, and one of them turns to the other one and says, oh, I just love this TDD stuff. Thanks for showing it to me. And the other programmer looks up at me. I just smiled. I thought that was fantastic. It's still not popular. People think that as soon as you can't think of how to test something, well, I guess I just can't use TDD for this at all. And this is maybe a good topic for future conversations, is moving into and out of TDD kind of workflow. Talk about other great impacts of TDD and clean code. Okay, so your programs have two sources of value. One is, if I just ran this, it costs me $1 to run the software, and people give me $2 for the outputs. And that's fantastic. That can scale very, very well, which makes it economically very valuable. But that's only one source of value. And eventually, competitors will come along, that source of value will dwindle. The other source of value is all the things that my software can do tomorrow. Last night I had a fantastic dinner with excited startup founders who were analyzing commercial satellite data for a particular application. And they were really excited about the application of it. And I said, yeah, but you know what's really cool? They said, no, what? I said, I don't either. But once you know how to analyze commercial satellite data at scale, you're going to find 20 different ways to use that, not just this first application. So software is this engine that takes dollars in and puts dollars out, usually quite profitable, but software is also this portfolio of options of what it can do next. And that's where TDD, clean code, the investments that you make into the structure of your software is all about those options that are created. If you have a big mess and you just don't even want to look at it, you're not going to think about all the things that it could do next. Somebody comes with a feature request and you say, oh God, we have to change this. We know we're going to break something. And so you don't have those options. But if you're like, okay, well, here comes a feature request, and it's really quite different than anything we've seen before, but it's related enough that we can implement that. That's fantastic. Now creativity is flowing, energy is flowing. You can try out lots of ideas, most of which will fail. The ones that succeed are going to succeed wildly, again with the power laws. So the more options you have, the bigger the area under that curve, and the more value that you can create. That's the economic argument for making investments in the structure of software. There's a human pride of work argument or aesthetic argument where geeks like writing beautiful code. It feels satisfying. You feel a sense of pride in what you're doing, and that's also valuable. Strategies do we have to reduce probability of avalanche besides decouple? That's it. With one caveat, the avalanche is just, it's gonna come. If I change this, I have to change all these things. Okay, if I restructure my application, all of my users have to change their behavior. Yeah, there is coupling there. That's a really expensive coupling to change, and there's nothing you can do about it. The one caveat is sometimes you can't see how to decouple, because every element in the system might be coupled to every other element of the system. And if you can't see how to decouple, sometimes you can reduce the scope of coupling. And that's what cohesion is. Cohesion is the degree to which inside of an element, if I change one thing, I have to change everything else. And that's good. Cohesion is good because it means that you don't have coupling at the next larger scale, which is a very short and poor explanation. I'm still working on this. This is why it's only been 15 years that I've been trying to explain cohesion, so I can't possibly have it down yet. But if you can't make progress on coupling, oftentimes you can make progress on cohesion, and that leads you to understand how to make progress on coupling. Another question. Struggle with starting projects and getting into those iterations because of non-functional security and everything else that's not programming takes so much time. When and how to approach non-functional requirements? I'll give you this is my unvarnished, unedited answer, which is ignore them until you can't ignore them. That seems like something like security. Like, really? Well, it depends. At Gusto, we're handling tons of personally identifiable information. We have bank accounts, we have social security numbers, we've got addresses, we know people's employment history. So our minimum security requirements are pretty intense. But we also improve security all the time. So it's not like we can't get security right and then now we can start iterating. Security is going to be part of that. So what is the reasonable baseline of security, and then how are we going to improve that over time? That lets me get started. It leaves me playing catch up, but that's always going to be true because of this. Every feature you implement is going to spawn 3 new features. Okay, so I'm always going to be playing catch up on performance. I'm always going to be playing catch up on resilience. I'm always going to be playing catch up on security. So let's get into that loop and realize that there's no such thing as done for any of those non-functional requirements. We're going to have to make investments. Sometimes those investments will grow. Sometimes those investments will shrink. But we can't ever treat them as things that are done. What that lets me do now is I think, well, all right, so what's a reasonable amount of security for my current situation? I have this poker user interface. Am I going to spend a lot of time proving a bunch of properties of the interface so that it can't be scraped for blah, blah, blah? No, it doesn't matter yet. When I can see it starting to matter, that's when I'm going to address it. That's how I get started. One of the things about experience, one of the bad things about experience is that the more experience you have, the more things you know can go wrong. If your reaction is, and I'm going to try and prevent those things from going wrong, then yeah, the non-functional requirements just get bigger and bigger and bigger, and you can't start anything. So I think one of the part of digesting that experience is realizing, okay, this is going to bite me on the butt later, and that's okay. This other thing that'll bite me on the butt later, and it's not okay. So I'm going to deal with that now. But this, yes, I know. Yes, we'll deal with it. And then let's get forward on the main path of learning that we have here. Oh, some people like to see the whole implementation laid out, and others prefer lots of cooperating small parts. Lumpers and splitters, I call these. The lumpers like to see everything in one place, and the splitters like to see lots of little pieces. You know what? You just gonna have to work that out. You're on a team, you're working together, you're gonna have to come to some place where you can agree. My bias is as a splitter. I want lots and lots of little pieces, and the collaboration of those pieces to create the behavior that I want to see. When I do that, I can separate the complexity out into little pieces. That's the only way that my brain can process a programming problem, is having the complexity divided up well. If I work with a lumper, I'm gonna have to adapt to some degree, and they're gonna have to adapt to some degree, because I can't work that way. I can't work with 100-line functions, 1,000-line functions. I just can't hold all that in my head at one time. So we're gonna have to come to some kind of agreement about how we're gonna work together. And that's why software design is an exercise in human relationships. Thank you so much for your time and your attention. Thank you for your support for Ukrainians. Deanna, thank you so much for sponsoring this. I really appreciate it.
Thank you so much, Kent. And thank you guys for attending this event. I just want to remember you that we're, by small things, we really make a lot of good stuff. So it was really, really great meetup. Thank you for your questions. If you have some questions, you can also find Kent in social media and also ask him there. So I hope to see you guys on other meetups, so we continue our projects to continue help Ukrainians and to unite our international community of developers around cool tech topics. So I just want to say you have a nice evening or day wherever you are, and hope to see you again.
Bye bye.
Yeah, bye.